All right. I hope you're ready because Henrik and Milos are going to tell you something about hacking RFIDs or attacking RFID chips. And they're both known for their community work for many years. For example, Sputnik and other RFID projects from 23.3 and other camps and events. All right, give the guys a warm welcome. Thank you.
Hi. We're going to talk about RFID, and because we know that there are often some misconceptions about what these cards are and what they are not, and what they can do and what they can't do. I'll start with an introduction into ISO 14443, which is the ISO standard for the most common type of RFID cards, or the most interesting type of RFID cards. It's an international standard for proximity integrated circuit cards, which basically means that, of course, it's an integrated circuit card. That's like smart cards you might know with contact, but these are contactless, and proximity means that the specified range is about 10 centimeters. There are other types of cards, like vicinity, which is, I think, 1 meter, and close coupling, which is 1 centimeter. But 14443 is about the proximity cards. Like some other standards for RFID cards, it works on 13.56 megahertz, which is a frequency which was free because nobody wants to use it because, for example, these welding machines work on the same frequency, and you can't really do another thing with it. The ISO 14443 is divided into 4 parts. Part 1 specifies the physical characteristics, which look just like the standard credit card size we all know, and also define how big the antenna must be and approximately where it has to be positioned. Part 2 specifies the radio frequency and the signal interface. For example, this will tell us how the power is transmitted to the card, because the card has no contacts, but also doesn't have a battery. It's a passive card, and we somehow must get power into that card. This is specified in part 2. I'll show later on a very simplified example of how that looks in a circuit diagram. Part 3 is the initialization and anti-collision procedure. I'll quickly cover that later too. And part 4 is one possible transmission protocol that you can run on these other layers. That's a layered approach. You can implement 1, 2, and 3, but don't have to implement 4. But if you want to implement 4, you have to implement 1, 2, and 3 also. In ISO 14443, there are actually 2 types of cards specified. That's type A and type B. Type A is basically the proprietary MyFair card standard from Philips, and they just put that into the standard. And type B is a different type. Type A is most common because it's MyFair and there are millions and millions of these cards. Type B is less common. Both of these types differ in the modulation and encoding that they use. Type B has a more complicated modulation scheme, which also transmits more power to the card, which means that if you have a card that needs a lot of power because it's doing a lot of cryptography, you are most likely take type B. That's why it's used in some of the electronic passports, but not all. I think about 30% of passports are type B. And most other cards that you'll encounter in daily life are type A. I've actually only seen about 2 type B cards in my life. and a lot of Type A cards. Now about the modulation scheme that's used from the actually the device, the reader device is called a proximity coupling device, PCD, and the card, as I already mentioned, is called a proximity integrated circuit card. And the modulation scheme from PCD to PICC, from the reader to the card, in Type A uses the simple amplitude shift keying, which is basically amplitude modulation. You switch the carrier on or you switch the carrier off. But as I already said, the card needs the carrier to generate its power, to get its power from, so you can only switch off the carrier for very, very short amounts of time. However, this modulation scheme is easy to receive because either the carrier is there or it's not there. You don't have to worry about the carrier changing its amplitude, as in Type B. Type B is 10% amplitude modulated, so you must distinguish whether the carrier is currently at 100% or at 110%, which is harder to do. For Type A, you just have to see whether the carrier is there or is not there, which can be done easily over a long range, depending on how good your receiver is, maybe 10 meters or more. And as you see, ich will die Maus bewegen. Nein. Wo willst du denn hin? As you can see, if you do the amplitude demodulation, this is basically the carrier strength. This is what data from the reader device to the card device looks like when you just look at the carrier strength. See carrier there, carrier not there, carrier there, carrier not there, and that's where the data is encoded. The reverse direction from the card to the reader device is different. That's because the card doesn't have a lot of power and it doesn't have a contact, so it uses load modulation, which basically means you can imagine that if you use for your model railroad at home a transformer to go from 200 volts to 12 volts, you will have two coils next to each other, and you induce a magnetic field, an alternating magnetic field in one of the coils, which will then induce voltage in the other coil. And that's basically just how these cards operate. The card antenna is just a coil inside the card, and the reader device has just a coil as an antenna, and you transfer power by induction. And the reverse direction to get data from the card to the reader device works by load modulation, which means that the card has a load, a resistor, which thus uses power and can switch that resistor on or off. There's a switch, well actually it's a transistor most likely, and if you switch the transistor on or off, it will take more or less power, and reversely that will be, you can detect that at the reader device. Just as you can at home, when you use that model railroad at home, when the train is moving, it's using power. That power must come from there somewhere. When it's not moving, it's not using power, and it's not getting power from the power grid. So you can measure whether the resistor is using power by just measuring the current. However, that signal is very weak. It's basically only an artifact of the power transmission. That means it's way below the carrier signal, about 60 or 80 decibels below the carrier signal. It's hard to receive, even over the short range that is specified. 10 centimeters is possible. It gets harder from there. Maybe you can, if you have a good antenna, do 50 centimeters. If you have very, very, very good equipment, you might be able to do 1 meter. But after that, it's pretty much impossible to receive the signal. So that was a quick introduction on how the carrier, how the power transmission and the data transmission works. Now to the context subject of anti-collision. As I said, part 3 specifies the anti-collision procedure, because if you have more than one card and put them in the field will power more than one card, and you somehow have to select which card you want to use. If you send something, you must specify to which card this is directed, and you'll have to know before that which cards are there. That's why ISO 14443 defines an anti-collision procedure, and the important thing about this anti-collision procedure is that every card needs a unique identifier. Doesn't have to be a fixed unique identifier, just needs to be reasonably unique. Either it's a fixed identifier that's programmed at the factory, or the card generates a random identifier on each time you put it into a field. That's what most passports do. I don't want to go too deep into this anti-collision procedure. Just remember that every card needs an anti-collision unique identifier, and it's transmitted in the clear. Now I want to say something about the different card types that you might encounter in daily life. As I said, most common are the MIFARE types. That's why I'm talking about these the most. Actually, most common RFID may not be MIFARE, but much dumber tags like electronic product code, or even these things, these very chips that you implant to your pets. But I don't find these particularly interesting. They usually don't have any security features and are just dumb storage for a couple of bits, while these MIFARE cards are nearly smart cards. They can store 1 to 4 kilobytes, maybe more, and have some intelligence to them, or maybe even the passports are even more intelligent, are also 4443 cards. The first MIFARE card type that I want to talk about is the MIFARE ultralight card, which is the simplest and most inexpensive MIFARE card type. That's designed to be used in tickets, in one-time use tickets, and disposable tickets, like, for example, for soccer games. The World Championships in 2006 used these type of chips in their tickets. The ultralight card has 46 bytes of storage, of which 10 bytes are read-only and programmed at the factory. 7 bytes of those are the unique identifier that's programmed at the factory. There are 6 bytes of programmable read-only memory that you can set from 0 to 1, but you can never set these bits back from 1 to 0. 2 of these bytes are used for log bits that you can if you set a log bit, then that means that some of the pages that the log bit refers to, will not be writable after that. That's what log bits are for. And then there are 48 bits remaining of usable memory that you can either write as often as you would like, or if you enable the log bits, then you can't write it anymore. The ultralight card is inexpensive because it doesn't have any encryption whatsoever. It has no security features, except maybe if you want to count the unique identifier as a security feature, then that might be a security feature. But as I said, it's transmitted in the clear, and you can easily fake it if you have the right equipment. That's the MIFARE ultralight memory layout. As you can see up here, the UID is stored. There are the CC, there are 2 check bytes over the UID to see whether it's transmitted correctly. There's 1 byte for internal use only. They don't say what it means. These are the log bits. They are only programmable ones. And there's an OTP area, one-time programmable memory, that you, for example, can use for single trip or multi-trip tickets. And you can, if you have a transportation system and you sell a card for 10 trips, you can use each of these bits for 1 trip and set it when the trip is being used, when the customer enters the train or whatever, and afterwards the bit can never be reset. So it's if you don't have the equipment to emulate that card, that might be secure. And there's the user area where you can write other cards, other things. The next type is the MIFARE Classic, which might be the most common card type. MIFARE Classic either has 1 kilobyte or 4 kilobytes of storage. The storage is organized into sectors, which are organized themselves into blocks, and each block has 16 bytes of storage. Each of these sectors has two keys, key A and key B. And in each sector there is the last block which stores the keys and some access control information. They have a pretty weird scheme to assign access control rights, but you can, for each of these two keys, assign different rights on different blocks in the sector. For example, you can say that key A might read the sector but not write it, and key B might write it and read it, or the other way around. Their security consists of a proprietary stream cipher they call Crypto1, which is a bit unfortunate because Crypto1 is a really bad word if you want to Google for it. There are hundreds of hits on Crypto1. All of those are introduction lectures to cryptography. They are all called Crypto1. And it's a proprietary stream cipher, which means nobody knows how the cipher works. And it's probably a bad cipher. It's already more than 10 years old, and their only security is security by obscurity because nobody knows the cipher. And the key size is also a laughable 48 bits, so you should be able to break it easily if you know the cipher. The communication in the air is encrypted with that cipher, and a session key that is generated while you are authentication through a challenge response authentication process. Each of these cards has a 4-byte UID, which is also used in the authentication process, and is also not changeable as most other UIDs. The MyFair card, classic card, is a lot of people like to use these MyFair classic cards for electronic purse applications because it has a special feature that you can, through the access control rights, declare that a block is a value block which stores some value, for example, monetary value. And then the interesting feature is that you cannot access this block using the standard write command to just write arbitrary things into that block, but instead you must use the increase and decrease commands, which add or subtract a value from that block. And then you can use the two keys and assign different right to the keys. And you can, through this mechanism, you can have a machine to increase. If you put cash money into the machine, hold your card in front of the machine will increase the amount that is stored on the card with one of the keys. And then you can have another key which only can decrease, and you can use that key for machines that don't need to be as secure as the other machine, which only can decrease the value that's stored on the card. And the MyFair Classic card, as I said, is divided into sectors, and each sector has 4 blocks. Actually, that differs between the cards. The last block stores the keys and the access control information, and there are up to 3 blocks of 16 bytes each for user area. And that's another interesting feature of the card. It's multi-application capable, which means that you can, each of these sectors has its own set of keys and they don't interfere with each other. You can store multiple things on that card without the owners of these things interfering with each other. You could have an access control application on the card which uses some blocks, some sectors, and one of these electronic purse applications which uses other sectors, and they won't interfere. The newer card type from MyFair is the Deathfire card, which is actually compatible to ISO 14453-4. All the other cards were only 14453-A3. The Deathfire card uses DES or triple DES for its security, has a 7-byte UID, but isn't very widely used up to now because it's also more expensive than the other types of cards. Another interesting card type is T = CL, which is the transmission protocol that is specified in ISO 14453-4 and specifies a way to transmit application protocol data units just like those that you know from the ISO 7816 cards, which are standard contact-based cards. You actually use the same protocol. which means that you don't have to specify a whole new set of commands. You just use the commands that are already specified in 7816, the commands such as select file, read binary, and so on. And you don't need to write new software. You just handle it in a driver that the card will look just like a contact-based card, and then you can reuse your old software that only knows about contact-based cards. The ISO 14443 doesn't specify security features for these cards, but instead you can just use the existing security features of 7816, which is the secure messaging of these standards. One example of these cards is are the electronic passports. And on the passports, the on-air transmission is either unencrypted because it's standard ISO 14443-4, or the electronic passports have a optional feature called basic access control, which uses the existing secure messaging standards. And after going through a challenge response authentication procedure, you will have a session key and then use triple DES or DES on the air channel to encrypt the data. There are other optional security features which may include other encryption techniques, but the important thing here is to remember that the data on air is encrypted, but the data on the card is not encrypted. General, the ICAO standards specify encryption as an optional feature, but nobody uses it because it's actually quite hard to use. You need to get the key to every reader device, and then you might just as well use no key because everyone knows the key. I'll now show some sniffing results that we have gathered from MyFair Classic cards. Milos will then explain some more about the process used to get these results, but I wanted to show them now so that you see what you will get. As far as I know, the MyFair Classic protocol is not publicly documented up to now, so this might be the first time yet that you see it. This is what we gathered using the sniffing device and then decoding the encoded data, the Manchester or modified Miller encoded data. And those are the frames that are actually transmitted on the air. You'll see that a frame is either a short frame of 7 bits or a standard frame of an arbitrary number of bytes. Maybe not arbitrary, but a number of bytes. What you'll also see is that it's always the reader sends something, then the card sends something. It's always request response. And this is actually what you see here, the anti-collision procedure up to here. This is a command that the reader uses to query whether there are any cards in the field. It just means, hello, any cards, please transmit that you are there. And our MyFair Classic card answers that she is there, it's there. Then the reader goes through the anti-collision loop, which is very short at this point because there are no collisions. This basically means all cards, please start transmitting your unique identifier now. Actually, not now, but there's a time defined after which the cards have to start to transmit their unique identifiers, and all cards that are in the field will then transmit their unique identifier simultaneously. This is what our card transmits. That's the card's unique identifier and a check byte. And the reader sees that there are no collisions, and then it sends card number B479F7D7ED. Please, you are selected, I'm talking to you now. To which the card will answer, and then it's selected, and all other cards that might be in the field will be mute after that. This is actually specified in ISO 14443-3. This is the anti-collision procedure specified there, and the following is the proprietary MyFair protocol that is not specified in any public standard. This is a frame in the last frame that is in the clear, and all the other frames are encrypted or something like that. That's why you might see that for some of these bytes the parity bit doesn't fit. Each of these bytes is transmitted with a parity bit, and each of the frames has a CRC at the end. And starting here, the CRC is not correct anymore, and the parity bits are also not correct anymore, which indicates that their encryption, their stream cipher, that they are using it for the parity bits and the CRC too, which is an interesting result. I'll show that in the next slide in more detail, or I'll explain in more detail. As I said, this is the recr command, which just means all card transmit, that you are there. That's the answer to request type A. That's the anticall command, which asks all cards to send their UID, and that's the UID of the card. Then the select and the select acknowledgement. This is all specified in the ISO 14403-3. And this is the proprietary MyFairBot protocol. As I said, this is probably in the authentication command. Authentication, the first authentication command, type A, for the key A, auth 1A. This is the block number that I want to authenticate to, which will be block 0. And there's the CRC. The CRC is correct. And then the card transmits something which we don't know what it is. It might be a random number. Then the reader transmits something of which we don't know what it is, but it's likely a hash of some sort over this random number and a second random number. And then the card transmits something which we don't know what it is, but it's likely a hash over the second random number. This is a standard challenge response authentication procedure, which is defined in ISO 9798-2, if I remember correctly. And after that, the session keys are established and all further communication is encrypted with the session keys. If you see here, this is probably the read command, the sector that I want to read, sector 0, and the CRC. And then the answer from the card, which is the 16 bytes of block 0 and 2 bytes for the CRC. So that was my short, or not so short, introduction, and now Milos will talk about some of the hardware aspects.
That's the intermission plane. It comes always after a break. Okay, I want to welcome you at this talk, and you may ask yourself, yeah, it's nice to hear that we can sniff data, but surely it must have been very difficult, and you need to be a rocket scientist to do so, and you need awfully expensive equipment and stuff like that. That's not true. Don't feel too safe. Basically, the required tool sets obviously span a broad range between very cheap hacks and very expensive tools needed. But plenty cards can be hacked with at very, very low cost. So what we want to show you in this introduction is that you can use your standard equipment for some types of RFID card, like your sound card in your PC, to analyze some types of RFID card and do your own research. And you maybe are not aware that how far single products of RFID vendors are spread around the world. For example, if you look at all these cards you use in your restaurant, your university, and whatever, they are mostly MyFair cards. Same goes for public transportation. RFID cards are also MyFair cards. So there are millions and millions of cards out there, and they are obviously protected by not knowing what's going on actually. So there is a vital interest of checking if someone can, for example, use your RFID card identity to spoof you and, for example, to take services at your public library, or, for example, commit crime in your name by placing false traces and stuff like that. So it's, I want to show you that it's a lot of fun. You just have to dare to enter this world, and it's a very beautiful playground. Okay, to prove my statement that it's very simple to start with RFID and to have a look by yourself and to be able to trust the products you already use. I want to show you a very nice hack of Henrik. This is my favorite hack in the RFID world because it shows the simplicity of an attack. This is actually an RFID sniffer. It's a piece of paper, basically. You only have a few turns, which are basically some rule of thumb, how many turns you have to do. These are simply glued with tape to the, you see a hand-drawn schematic of the circuit, which consists of exactly 3 parts, which is the coil, the diode for rectification, and a capacitor for smoothing the resulting signal. And this you can simply connect to your PC and you can immediately start sniffing 100 kilohertz RFID tags. So they are very widespread in door systems, for example, or for example in key fobs for cars. So you can just spend a few cents on parts and you have a perfect RFID sniffer. And the average sound card does the job. You may think that this is already cool, but it's much, much cooler. Henrik did a second device. As you see, same concept, same paper, same coil. You see only one device more, which is a MOSFET. You have to think of a MOSFET like a relay, where you set power to it and it just shorts the circuit. This is used to emulate a RFID card. Okay, you may think these two things are cool, but you have to imagine this thing plugged to an iPod, recording an RFID transmission, and then replaying the very same transmission by using the very same iPod, and clack, the door opens. So this is, in my opinion, the coolest hack ever. Okay, so you have no excuse not to take part in RFID security research. Okay, the next step is some of you may have an oscilloscope. The problem is that with higher bit rates, your average sound card isn't fast enough. Average sound card can sample at 48 kilohertz, so you basically can sample data up to 24 kilohertz, which is exactly half of the sampling rate you have in your card. So to examine this high-end cards like MyFair, which work in 13.56 megahertz range, basically the antenna is the very same. I think, to my opinion, antennas, RFID antennas don't deserve the name RFID antenna because it's in fact no antenna at all. Like Henrik already explained, it's basically one end of a transformer, and that's all. So it's very simple to build. You may have fear of building antennas because there's always foo spread around building antennas, and there is a lot of secrecy around. But building an RFID antenna is very, very simple because you basically build a transformer. You don't even need a core or something like that. So the most simple antenna you can imagine is just you take your oscilloscope probe, take your ground connector and just connect it to the pin of your probe. That's all. This single loop, it's obviously not tuned, nothing. It's already a very good loop antenna. You can immediately start sniffing RFID signals with a simple oscilloscope. It's a bit hairy to find the trigger level, but as you can see, you see a very nice picture, and with some practice, you can immediately read the bits that are transmitted. And this is definitely possible. It took me, say, several hours to figure it out because I'm not that fast, but I think you can figure it out much faster. Yeah. Okay, this is basically what I said. You just place this loop antenna between your RFID reader and between your card. The point is that if you want to attack a specific RFID system, you don't know if it's one in the 100 kilohertz range or if it's one in the 13.56 megahertz range. To find this out, it's the most simple way is not to play around, but to simply take an oscilloscope or frequency counter. This would be also enough. You can build a frequency counter very simple by using, there are cheap ICs available that do counting and just use the least significant bit for letting an LED blink, and you immediately see if it's a 100 kilohertz carrier or if it's a 13.56 megahertz carrier. So also no excuse for equipment prices. For testing and get quick results, I suggest you to take a known system and make constant transmission and try to get a feeling about how adjusting the trigger level. And you will see it's very, very simple. Okay, with the data you see, you can, by figuring out what modulation patterns are used, what type of card you have, and then you can use your RFID reader to access this card. And you can verify if it's a well-known card at all. There are plenty of RFID cards out there which are not documented at all, and they are probably can be hacked easily because nobody yet tried to hack them at all. So it's definitely worth to have a look what happens on the air. A very nice check which can be simply done is you simply look how long the transaction is. Most RFID, or some, no, most is wrong, they learned a bit in the last years, but I say more than half of the RFID door systems out there still work on a UID-based scheme, because the common knowledge is that you can buy one card and you can't buy the second card with the same UID. So it's widely regarded as a security scheme to just check for the UID. But obviously, you already saw it in Henrik's part, the UID is not protected against reading. So you once sniff a valid RFID UID, you can sniff this over range because you don't have the intention to influence the rear field, and then you can just take your simple device and replay it, obviously with the proper timing, but this is no security system. So what if you want to implement such a system on your own? Then you want to stick to a cryptographically secured card, and even MyFair standard is much better than a UID-based scheme, obviously, at least till we find out how Crypto One works. But you have to make sure that there is a authentication between reader and the card. And if you see that only few bytes are transmitted, then it's not possible to do such an authentication. Maybe they do some foobar, and you have to sample some test samples, and you can reply accordingly without even knowing what the protocol actually means. Okay, so short transactions are clear indication of that something going wrong. You also can see if the packets are changing with each transaction, because this is a clear indication that we are talking probably about a cryptographic implementation. So this can be also verified by using a cheap oscilloscope. Okay, I want to dive deeper into building loop antennas. As Henrik already shows, loop antennas are very simple, and basically, to a given radius at least, you can, by increasing the diameter of the loop antenna, you can increase the range directly. So there is a certain limit. I won't go deeper into that, but to a certain level you can increase it, and you can build this cheaply. So in the worst case, you just take some 2 pieces of wood and build just a bigger loop, and that's all. To increase the gain of the antenna, you must tune it. So if you tune it into resonancy, then you get a much higher range. The range quickly increases by a factor of 4. So it's definitely worth to tune your antenna, and tuning your antenna sounds difficult, but it isn't. In fact, you can because you're only sniffing and not transmitting, you can buy very cheap capacitors that are tunable and just plug in one end of your antenna, and you can use a simple voltmeter to check where the resonant frequency is. And it's a pretty sharp tuning, but you can, for example, by adding two capacitors in parallel, one very small tunable capacitor, one huge capacitor, you can tune in the rough area, and then you can fine tune with the small capacitor. So there is no rocket science behind it. So just try it. If you want to do serious attacks with long range, obviously you want to have as few noise as possible. You can buy ready-made operation amplifiers, which come in, even if you are not so good in soldering, they come in this dip housing that you can stick in breadboards. It's very simple, and you put them as near as possible to the antenna and just buffer the signal for a starter. So it's a very, very simple circuit. Yeah, and if you want to see how such an FHF example of such an FHF front end, you want to have a look at the OpenPICC schematics. OpenPICC, I will explain it later, is our RFID sniffer and soon to be RFID emulator. So just take the HF front end, there is already proven, so you can just copy and paste it. If you want to do high sophisticated attacks where you want to correlate multiple samples, which is also a nice possibility to get rid of all the noise, you just sample, say, if you're lucky and you have a transaction which is basically mostly the same, you can sample it 10, 100 times, million times, how often you want, and then just by overlaying it, you get rid of all the noise. So this is very simple, and if you are not so good in programming, you can even do it in Star Office or in OpenOffice with a spreadsheet. So there is also no rocket science behind it. Okay, and a very nice tool which I can highly suggest you is GNU Radio. We love it very much. You probably will look on the website of GNU Radio and will find out that you think that's fucking expensive, but it's very cheap, in fact. It's around 700 euros, but it replaces a whole set of tools. It's a highly sophisticated spectrum analyzer. You can capture any frequencies up to the gigahertz range. You can replay any frequencies up to the gigahertz range. You can use any modulation patterns you want. And the nice thing is that you do everything in software. You don't need to solder anything. You just have GNU Radio, have a nice set of Python objects, just connect them, and they usually do what you want. GNU Radio is very powerful. It can even decode HDTV transmissions. So it's a perfect tool if you want to find out what's going on also in other RF protocols. And yeah, you get very quick results with this. So to be able to make a security evaluation more simple, there was one option to reverse engineer existing reader, but we said, oh no, we don't want to do this, because usually after you reverse engineer something, half a year later you have to buy the next one because it's not on stock anymore, and you start from scratch. So we decided to build our own reader, which is optimized for security evaluations. So basically we build a reader which uses a common chipset, RC632 from NXP, and it basically does most of the work and the hairy work on RFID, 13.56 megahertz protocols, and the nice thing is it also supports MyFair. So this a proprietary protocol Henrik mentioned before is inside this chip. So you have a very nice system where you have a black box where you put data on one side in, and on the other side you can analyze it. So and to make sure that it's community compatible, we make sure that you don't need any special programming equipment. You just use your Linux PC. You have a standard ARM toolchain. It's a 32-bit ARM controller. Harold Welter created a very great library called librfid, which was originally made for a commercial reader, but then we quickly ported it to our reader. By the way, he also made a very nice library for reading electronic travel documents which is stacks on top on librfid. So the nice thing on this 32-bit ARM processor is that it allows standalone operation. So Harold ported librfid to this 32-bit ARM processor, and it runs completely self-contained within our reader if you want. Usually you use the dump reader firmware image, which just forwards requests for application software because it's easier to debug. But as soon as your system is working, you can just by cross-compiling it, you can run it inside the reader itself. So just by powering over battery, you have a mobile reader that doesn't need a laptop and stuff like that. And for those that have the equipment, but I personally didn't use it, you can even debug with a JTAG interface, and there are some extension ports where you can add your own hardware. For example, if you want to create a door security system and stuff like that. So the idea to make the security evaluations easier is that we made possible that we can sample each data that is transmitted on the RF interface synchronously to the carrier, because this is part of most standards that you have to reply within this and this carrier cycles and so on. So to remove this problem from software, we just use the internal timer to divide the carrier frequency down to any level you want. You can shift the phase wherever you want, and the DMA system makes sure that the bits are precisely sampled at the time you intend. Same goes for outgoing signals. So basically this RC632 provides a mode where you can just toggle one of its I/O pins and create any bit pattern you want as a modulation. So this means that the reader can be used to talk to any proprietary card as soon as you know how the protocol works. So as soon as you find out how the protocol works, you don't need a proprietary reader for the specific card, but you can reprogram OpenPCD to support this particular card, even when it's not supported by the RC632. For checking the performance of your homegrown antennas, there is a mode where you can send out constant modulation patterns, so you see how smooth your edges are and how high the bit rates are that are supported by your antenna, because there are some beginner mistakes where you add too high capacitors and your all data is eroded to nothing, so you don't see anything. So with this tool you have a serial terminal where you can toggle the speeds and the modulation depths. So you see, for example, if you are all able to sniff what's pretty hairy, this B-type cards. Okay, and the counterpart is OpenPICC. Just to make it cool, we made sure that it's also RFID card sized, and it is intended to be accurate emulation, often a passive RFID card. And to make it easier, we just used external power supply, in this case the USB connector, and so we can afford a much faster processor than it's usually used inside this RFID cards, because we have our own power supply and the reader doesn't see the difference. So again, there is the very same processor, the 32-bit ARM based CPU with basically the same operating system. Again, standalone operation is possible, so as long as you find out how the system works, you implement in software, you have something that is the size of a RFID card and exactly looks like an RFID card. So For emulation, our first goal is to emulate MIFARE ultralight, because this is already well documented and many systems rely on the fact that the UID can't be changed. So obviously if you emulate it in software, you can use every UID you want. And it again has RS-232 interface like OpenPCD, where you can connect a serial interface to see what's going on and to send out debug messages or provide a serial terminal for modifying the behavior. We already have a nice firmware that is the counterpart of OpenPCD, where you can send out load modulations pattern synchronously to the carrier. So again, you can check if the return communication can be also sniffed accurately by your setup. Again, it has a JTAG debug interface. You just have to solder a 20-pin header to it, and I2C for custom extensions. And I think I don't go deeper into it. It's the very same. You have again DMA acceleration. You have to narrow down the data. We quickly convert it into binary levels. We have a DA converter that creates a compare voltage, and everything that's above the voltage will result in a 1. Everything that is below the voltage will result in 0. So you can, if you try to sniff on longer ranges, you can adjust the threshold. Again, you can send 3-bit patterns at DMA accelerated. The only difference is that the RFID card completely relies on the carrier clock. Everything has to be done synchronously, and to get the same pictures when sniffing, like you see in the books and on oscilloscope, we made sure that the carrier is still simulated during modulation pauses, because if you have no modulation, then you have obviously no carrier. Then you can't, for example, clock your DMA. So we made sure that we added a PLL, that it's always stopped when there is a modulation pause, but during the modulation pause it provides ongoing the very same frequency like before, and afterwards when the modulation pause is over, the PLL again adjusts to the carrier. And this makes sure if you sniff that you see the very same waveforms of the demodulated signal like on your oscilloscope. We already have nice application software for logging and decoding RFID reader to tag communication with OpenPICC. So this basically, you can see it on our website. There is a short introduction how to use OpenPICC to sniff reader to tag communication. Okay, and interesting. Obviously, it's interesting to combine both devices. You can, if you combine them, connect them by using this GTL-based serial interface. They can talk to each other, and you can create a device that can read, for example, MIFARE ultralight card, and as soon as we have the emulation profile, OpenPICC can emulate the very same card, and you don't need any computer hardware for this. So you can get a handheld device where you just point and you have a copy of the card, and you can use it like a card. But as I said, we currently work on the anti-collision still. It's had a very low priority in the last months because we're busy with other projects. But as soon as we have the anti-collision, it's very simple to create emulated cards, because basically the only real-time critical part on the card reader card transaction is the anti-collision. As soon as anti-collision is over, it's even possible to do the higher level communication directly over your PC. So basically OpenPICC can emulate the time critical parts, and for development purposes you can run the emulation profile on your PC, and you can debug it and whatever. And as soon as you verify that your emulation image works, you can cross-compile it again and have it run inside OpenPICC. We currently, the users we had for OpenPICC, we used to gather the encrypted MIFARE communication you saw before, And what we want to do, because we are not cryptographers at all, we have basically no clue about this. We want to make it possible for others that have no clue about hardware to get the computed data with the proper bytecodes, with the verified CRCs, and to run crypto analysis against it. And to our opinion, we provide a huge stack of sampled transactions with known keys, and I think this is a good start for the cryptographic community to cryptanalyze this algorithm, and then we find out how secure it actually is. Also nice feature is the anti-collusion. Basically, you already saw it in Henrik's part, is used to singularize one card of many. So the practical limit with real cards is that with a given amount of cards, the reader field isn't strong enough anymore to support the cards, even when they are sleeping. But with OpenPICC, you can have one device that looks like, say, 1,000 cards or 1 million cards or 1 billion cards. So if the reader still tries to check the whole tree of cards, then it obviously breaks, and it's basically some kind of denial of service attack. So this could be a nice protection device. But others done already very nice work in this area. Maybe Henrik want to explain?
Yeah, we had that at the last Congress, the RFID Guardian, if I remember correctly, from the group of from Amsterdam. Melanie Ryback held a presentation. You can look it up in the Congress archives. They have a device for this purpose.
Okay, and also very nice use for OpenPICCs, because all the stuff is done in software. You can change every aspect of the protocol. You can add one bit at the end, you can change the length of UID, you can try to break the anti-collusion, and it would be very nice to implement the fuzzing suite with OpenPICC, which could test for errors in the reader firmware, because usually in current RFID readers, the reader firmware is very high level. It already does a lot of stuff, and usually the application level software relies that the underlying reader software has done a proper job, but as you know, shit happens. So this would be also nice use for OpenPICC. So our to-do list. We want to get finally anti-collusion running. It's very important to do any emulation at all. We could do without anti-collusion, but then it's no proper RFID card, because you would basically make some assumptions that are only true for particular readers. So we definitely need anti-collusion to make it usable for generic use. Like I said, provide tons of samples for people that are not so good in hardware and gathering all the samples, but they are much better in mathematics and cryptanalysis, to get them something to work with. And we are very open, for example, if you have specific requirements for keys you want to get samples, we will sample them for you. So just send us the keys you want to get the cryptographic transaction for. We will make the samples for you, so don't worry. You can do it in your favorite tools, and you don't need to touch any hardware at all. We will help you gladly, because we can't do it at all. Yeah, and we came to the conclusion that OpenPCD is maybe a very nice tool, but we found out that only very few people actively participate in the development, and we think the problem is that we wrote basically our own operating system, and we think that maybe this distracts people from learning another operating system again and to dive into our hack code. So as we did already for Open Beacon project, we now use publicly available operating system called FreeRTOS, which is very, very cool. It has a very small footprint, you can do multitasking, you have semaphores, you have everything you want and you have already in huge operating systems. So, and it has a big community and good documentation. So by throwing all our code away and porting everything to FreeRTOS, we hope that we attract you more to add your own code, because for average programmers it's much simpler to do anything, because you just start a background task and do whatever you want in background, and you don't have to care about interrupt levels and stuff like that. So I think it would be much easier for you, for example, to create your own emulation software, because for open PICC currently you need, in my guessing, around 1 week to understand what's actually going on before you are able to start coding at all. So hopefully you will respond to our additional efforts. Okay, thanks you for listening, and we hope you have many questions, and we are gladly to answer your questions. We offer tomorrow hands-on hacking if you're interested. So if you want to see the stuff running actually, you can join us at Art of Beauty area, and we can show you how these things work practically, and you can play around with the equipment.
We'll announce.
Yeah.
And also I have a personal request. I like to play with RFID cards, especially electronic passports. So if any of you has one of these, it would be very nice for you to contact me. My DECT phone number is 5015, or you can grab me just now. I'd really like to look at your passport or other cards. Questions, or is it too late? Apparently. Da. Jetzt ist sie.
Warte mal ein bisschen.
Test. Can you tell me if you wanted current passport, and if I give it my current passport to you, will I still be able to get back home?
Yeah, what Henrik is currently working on is a very cool piece of software. Like you heard in his part before, most passports have a random ID, so you can't easily figure out what identity the user is, because each time you start a new reading and turn on the reader field, you get a new ID. So you don't see, for example, which country the person is from. So what Henrik wants to achieve is a piece of software that fingerprints all available information to the outside and tries to estimate what happens. So Henrik will not store the information. We will only use it for gathering more data for his pool of fingerprint attacks. So we won't give you the data away. It will be erased safely, and you have to be aware that on one side the electronic passport are you have to regard them like USB sticks. You just store data on them, but the data is guarded within, it's signed by itself. So you can't create a fake passport with a different name or whatever based on your passport data, or with another picture or something like that. So this is not possible. This is guarded with well-known algorithms which are currently regarded as unbreakable, and we agree to this opinion. So I hope you will trust us, because we badly need the data to increase our pool for fingerprinting, because this is if we find out, and there are clear indications for this, that you can fingerprint the nationality of a person, then it's obviously a big security threat. So by documenting the security threat, you all will be saved from country-specific attacks. So it's for the greater good. So hope you will join us.
More questions?
Okay, if you have more questions, we will now go to our booth at Art and Beauty, and then we can have a nice chat.